Thank you. It's a great pleasure to be here. And what I'd like to discuss today are aspects of work that I do research on, solar system, how we form the Earth, how we form planetary systems in general. And the main topic of tonight's talk will be, what have we learnt about the formation of planets from the discovery of extrasolar planets? So I think, as many of you know, in the last 20 or 25 years, we've now discovered a very large number of extrasolar planetary systems, maybe 4,000 or more planets beyond the solar system. So the question I'd like to ask and try to answer tonight is, what has that abundance of planetary systems told us about, in general, how planetary systems form? So let's start, though, closer to home and start thinking about the solar system. And of course, we know an enormous amount about the solar system. So spacecraft have visited all of the planets and quite a number of the smaller bodies in the solar system, and we know a tremendous amount of detailed properties about those objects. But if you sort of step back and ask, what are the most basic properties of the solar system that tell us something about perhaps how the planets formed, I would say there's sort of two things. The first is that we have two classes of planets in the solar system. We have the terrestrial planets, Mercury, Venus, Earth, and Mars, which are small rocky bodies. And then we have the giant planets. We have the two gas giants, Jupiter and Saturn, and then we have the two smaller ice giants, Uranus and Neptune. And in the solar system, we have a very distinctive architecture where the terrestrial planets, the rocky planets, are distinctly close to the Sun, whereas the giant planets are all in the outer regions of the planetary system. And then, of course, zooming in, if we're interested in habitability and life, the situation in the solar system is very well known. We have one planet, the Earth, which has abundant liquid water on the surface and abundant life. We have Mars, where currently Mars does not appear to be a very habitable planet, but we have quite a large amount of evidence that in the past there was at least running water and possibly habitable conditions on Mars. And then we have some smaller bodies where there's no liquid water on the surface because bodies are too small, they're too cold, but where we have a reasonable amount of evidence for subsurface oceans, which again potentially could be sites of life. What you're seeing here is an image of Saturn's moon, Enceladus, but there's also Jupiter's moon, large moon, Europa, which is in the same category. So the questions we're going to try to answer tonight are sort of the big questions that are to do with planetary systems. So what you're looking at here is an image of the sky from the Gaia mission, which mapped about 2 billion stars in the galaxy. So this is still a small fraction of the total number of stars within the galaxy. So we know that planets are common around these stars, but the questions we want to ask are, how common are planetary systems like the solar system? Is the solar system a sort of typical example of a planetary system? Or is it an atypical example of a planetary system? How common are potentially habitable planets like Earth? And then, of course, ultimately looking towards the future, we'd like to say something about how common planets are that have really habitable conditions and potentially have life. So where do we start? Well, we start with where the protoplanetary disks that give rise to planetary systems come from. And these come ultimately from the regions of star formation that we see within our galaxy. So this is the Orion Nebula. It's a nearby region of star formation to the Earth, which you can see very easily with a small telescope. And what you have here is dense gas that is potentially unstable to collapsing to form new stars. And we can do computer simulations of how that process might work. And this is what's being shown here, where you take a large amount of gas that's massive and turbulent, and you allow it to collapse under its own weight, under its own gravity, to start to form stars. And because the initial gas that you start with is turbulent, it's been stirred up perhaps by supernova explosions and so forth in the galaxy, what you get is not just one star or a binary star, but you typically get a whole cluster of stars. And this is very commonly how stars are forming within the galaxy. And around each star, as the remaining gas falls in, that gas sort of misses the surface of the star, and it starts to form rotationally supported disks around those stars. And that's what you're seeing in this computer simulation here. You're seeing the formation of stars, and then as more gas falls in, the formation of what would be protoplanetary disks around those stars. And you can see there's some complicated dynamics here. Some of the stars are approaching each other closely. They're disrupting and interacting with each other's disks. It's a complicated and turbulent situation. But the end result will be stars surrounded by disks on a timescale that's relatively short by astronomical standards. We might be talking a few hundreds of thousands of years for one of these large gas clouds to collapse and form a cluster of stars surrounded by disks. And in more recent years, we've been able to actually observe some of these disks at high resolution. So this is one particularly spectacular example that's been seen in just the last few years. This is the HL Tau system, which is a young star surrounded by a disk relatively close to the Sun. And here it's being observed in radio waves with wavelengths that are about 1 millimeter. And what that observation is showing us is the distribution of relatively small dust grains around that star. So you can think of this as being a star. It's surrounded by an orbiting gas disk, but then within that gas disk, there are little particles of dust that maybe have grown up to be about the size of 1 millimeter. So small macroscopic dust particles. What you can see here is that the disk is basically circular, but it's not smooth. It seems to have these rings, seems to resemble perhaps something like a much larger version of Saturn's rings in the solar system. Here's another observation, this time not made with a radio telescope, but made with an optical telescope, made with the Hubble Space Telescope. Here what you're looking at is a disk seen almost edge-on. So you can't actually see the star here because the dust and gas in the disk has blocked the starlight from our view on Earth. Instead, what you can see is some light which has been scattered from the upper and lower surfaces of the disk, and then you can actually see a jet of material which is being accelerated somehow very close to the star and is blasting back into the interstellar medium around the star. And from these kind of observations, we can infer some basic things about how planet formation must take place. We know that these gas disks and the dust that's within them lives typically for a few million years. So that sets the amount of time we have available for building at least the gas giant planets which contain significant amounts of gas. For the terrestrial planets, things like the Earth, which don't have large amounts of gas, potentially their formation window could extend longer because they could form after the gas had actually been lost. And this timescale of a few million years is about the same timescale as we infer from studying meteorites on Earth and understanding from radioactive dating how long that material took to assemble in the solar nebula. So how did these planets form? Well, to a large extent, we're still working today based on a paradigm that was originally developed in the 1960s by Viktor Safronov, who's shown here. And so he published a very famous book at the end of the 1960s, The Evolution of the Protoplanetary Cloud and Formation of the Earth and the Planets, which set out the basic theoretical ideas that now underlie planet formation. And I should say this was really a remarkable achievement because all of those observations of disks around stars, of stars forming in our own galaxy, those were not things which were available to astronomers in the 1960s. So the only evidence that Safronov had in developing this theory was some evidence, of course, from the solar system and general theoretical or physics considerations about what must be going on. So the theory Safronov developed is sometimes described as the planetesimal theory of planet formation because it starts with building blocks that are not dust particles, not very small particles of dust around stars, but really rather are larger building blocks. And these are objects that we describe as planetesimals. And primordial planetesimals you could think of as being perhaps kilometer-sized analogues of the asteroids and comets that we see in the solar system. So the image here is the comet that was seen by the Rosetta spacecraft. This may well not be a primordial object, but the primordial planetesimals perhaps would have looked something like this. And in Safronov's theory, they were typically of the size of kilometers. So how would this have worked? Well, in Safronov's model, the planetesimals would have been spread throughout the solar system, throughout the primordial solar system. However, there's a special location in the solar system which is described as the snow line. So if you imagine going out in the protoplanetary disk from the young sun, the temperature, of course, would have been high, close to the sun, and it would have dropped off as you moved further away towards the outer regions of the planetary system. And this snow line represents a dividing line. Inside the snow line, the planetesimals would have been made up of rock, and the water, which would have been abundant in the protoplanetary disk, would have been in the form of water vapor. So that water vapor would have not been able to be accumulated within rocks and to start forming larger objects. If, on the other hand, we go outside the snow line, we would have had rock, but then we would have also had water in the form of ice. And because hydrogen and oxygen, the components of water, are very abundant elements in the universe, when you have both rock and water ice, you have a much larger reservoir of solid material than when you just have rock on its own. And that ratio is something like a factor of 3. And in Safronov's theory, that ratio, that increase in material when you go beyond the snow line, turns out to have a very important implication, which we'll come to, for the structure of the planetary system that comes out at the end. Now, where was this snow line in the solar nebula? Well, we can infer this by looking at actually the properties of meteorites which have come from the asteroid belt. So if we look from meteorites that come from the inner part of the asteroid belt, we can observe those meteorites, or we can measure those meteorites in the lab, and then we can match them up to asteroids which have similar colors that are still orbiting in the asteroid belt. And what we find is that the asteroids and the meteorites that come from the inner belt are made up of minerals that have very small amounts of water within them. So they're, if you like, dry materials from the inner asteroid belt. Whereas the meteorites that come from the outer belt contain significant amounts of water. So they're, if you like, wet minerals coming from the outer asteroid belt. So we think that the snow line, when the solar system was forming, lay roughly in the middle of where the asteroid belt is today. And the consequence of that, of course, is that the main materials that formed the Earth were well inside the snow line, and so the amount of water that was contained in them was relatively little. So the Earth itself, we think, basically formed dry, even though today, perhaps, we associate water very strongly with the Earth as a planet. Okay, so here's an illustration of how that process may have worked. How did those primordial planetesimals grow as they collided together under gravity? Let's see if we can play this movie. So the picture is that we started with a large distribution of planetesimals that were spread out to the inner part of the solar system. And the ones close to the sun were dry, those are color-coded red here, and the ones that were further out were made out of these minerals that contained water. And over time, gravity caused those planetesimals to collide and to grow into successively larger objects. So sort of small objects, maybe the size of the moon, and then ultimately larger planets like the Earth and Venus. And you can see this process playing out in a computer simulation here. Here's distance from the center of the sun, center of the solar system. So you can see this process playing out, and the planet formation occurs more quickly in the inner part of the solar system because the timescales for the orbits there are much shorter. But then as time goes on, the planets in the inner part grow larger, and what you can maybe see is a mixing of the water-poor material in the inner part of the planetary system and the water-rich material, which ultimately came from the asteroid belt, as time proceeds. And what we think is that in the solar system, this process would have run to completion for the terrestrial planets in something like 100 million years. So you see the time counter on the top there. At about 100 million years, most of this small material has been accreted, and what we've been left with is a small number of terrestrial planets with sort of properties that can be made to roughly match those which we see in the solar system. And in this story, the water that we now have on Earth is ultimately delivered from the outer regions of the asteroid belt. Here's just another representation of that. Again, you can see these objects colliding amongst each other and growing larger, and then as time goes on, an initially smooth distribution of many bodies is accumulating into a small number of massive bodies. So this is a model which can explain roughly the properties of the terrestrial planets. It's not perfect. There are some aspects, for example, the mass of Mars, which is predicted in these theories, is not quite the same as the real Mars, but in a broad sense, it gives a representation of what we think we see in the solar system. Now, what about when we go beyond the snow line? I said beyond the snow line, there was a larger amount of material, a larger reservoir of material available for forming planets. So, beyond the snow line, having that larger amount of material, it's easier to grow massive objects on a relatively short time scale. And what we think happened is that beyond the snow line, roughly where Jupiter is in the solar system today, you were able to build objects that were maybe 5 or 20 times the mass of the Earth on a time scale of just a few million years. And if you remember that the gas in the protoplanetary disk lasted for a few million years, that means that those massive objects, those planetary cores as we call them, were able to capture gas in the protoplanetary disk before that gas was dissipated from the young sun. And that's how we think we then formed the gas giants. We formed Jupiter, and we formed Saturn. Here's just an actual calculation of that process, showing how over time, the mass in both the planetary core and then the planetary envelope might have assembled as that material collided together. So what happens first is that you build this core of maybe, as I say, 5, 10, 20 times the mass of the Earth.
Initially, that's surrounded by an atmosphere of maybe just a few Earth masses of gas, but over time, more gas comes in from the protoplanetary disk, and eventually you reach a runaway phase where gas falls in at really a rapid rate and builds the gas giants that we see today. So something like Jupiter would be a planet that had got to the end of this process. Something like Uranus and Neptune would be a planet, perhaps that was in this intermediate stage. We had a large core of rock and ice, and maybe a very significant atmosphere, maybe several Earth masses of gas around it, but not yet a full gas giant. Okay, so that's the basic theory we have for what happened in the solar system, and it's quite a compelling theory because it can actually explain these basic observations of what we see in the solar system. It can explain why we have small rocky planets inside the snow line, but much larger objects outside. That's connected to the abundance of the material that ultimately formed the planets. And it can explain why the Earth has a significant amount of water, but is not completely dominated by water. It's not a water world made up of 50, 60, 70% of water. Okay. But despite that, there are some mysteries. I've already mentioned that there are some mysteries in the solar system, so things like the mass of Mars are aspects that are still not fully understood. There are some theoretical mysteries, some parts of the process which are not fully understood, and then there are some other mysteries which are coming from extrasolar planets. So I'm going to go through some of those in that order. So to start with a theoretical mystery, there's a question of where do the planetesimals, which make up the building blocks of this theory, actually come from in the first place. So when we really observe protoplanetary disks, there's that beautiful image of HL Tau on the left, what we're seeing in terms of solid material is really very small particles. So dust particles that maybe range in size from just millionths of a meter up to things that are maybe millimeters in size. Okay? So these are very small particles of dust. To go from millimeter-sized particles to planetesimals, which are maybe kilometers in size, we have to go 1 million times in size scale and 1 million cubed in mass scale. So there's a very large range of size and mass scales between what we really directly observe and then the building blocks of this relatively successful theory at a later stage. Now, one might think that the way this happens is sort of straightforward. You take a lot of dust, it's colliding together within the gas. The millimeter-sized particles are colliding to become 2 millimeter-sized particles. Those are then colliding with other particles to become bigger, and you just have a succession of these pairwise collisions to ultimately make planetesimals. But we think that's actually probably not what happened, because when we do lab experiments, what you're looking at here is experiments done in low-gravity environments where you collide particles with compositions similar to what we think were present in the solar nebula. You find that material that would have been within the snow line is actually not very sticky. So if you form perhaps millimeter-sized particles of dust in the inner part of the planetary system, when those millimeter-sized particles of rock collide, they tend to bounce or fragment or disrupt each other rather than sticking to grow larger objects. So that might not be true for icy particles that are far out in the planetary system, but at least inside the snow line, it seems that the materials we have are simply not sticky enough to grow planetesimals directly. So instead, we have other theories for what might be going on. This is showing again the results of computer simulations. We think that in the environment where we have both gas and dust, the gas and dust are coupled by aerodynamic forces. And what we find is that those forces can give rise to new instabilities which can cause the dust particles, or the pebbles perhaps, to clump together very strongly. And that's what you're seeing here. You're seeing a visualization of solid material embedded within a gas disk where the solids are clumping together to form massive clumps of pebble-sized objects. And the idea is simply that these clumps can become so massive that they can collapse under their own gravity, under their own weight, to directly form planetesimals on quite a short time scale. And if this is what's going on to form planetesimals, this time scale can really be quite short. In the region where the Earth is today, we might be talking about building these kilometer-sized or even larger than that objects in just hundreds of years from these very large clumps of pebbles. Now, if that is what's going on, there are some interesting consequences. What we find is that when you do calculations of that, the primordial planetesimals you form are significantly larger than was assumed in these original models of planet formation. The largest objects that are formed that way might be hundreds of kilometers in size, so they might actually be comparable in size to large asteroids that we see today in the asteroid belt. Here's Ceres, one of the largest asteroids, the largest asteroid in the asteroid belt. Okay, so that's a theoretical puzzle. What about the issue of extrasolar planetary systems? So these actually pose several related but different puzzles for planet formation. And I want to discuss sort of separately issues that are raised by observations of giant planets and those that are raised from observations of smaller planets with masses more comparable to the Earth. And the basic puzzles are that when we look at the giant planets, it's their orbits which appear to be unusual and different from what we see in the solar system. So in a number of ways, which we'll discuss, the orbits of giant planets are frequently quite unlike anything that we see in the solar system. Now, when we go to the lower mass planets, which might have masses between an Earth mass and maybe 10 times the mass of the Earth, it's not the orbits so much that are the issue, but the compositions or the inferred compositions of those planets. And as we'll see, the probable composition of many of those planets appear to be quite different from any planet that we see in the solar system. So there's a basic question there of what is the nature of those worlds, given that we don't have terrestrial analogues, solar system analogues of those systems. So let's start with the giant planets. And so here we're thinking about planets you might loosely call extrasolar Saturns, up to extrasolar Jupiters, up to planets that are maybe several times the mass of Jupiter. So these we think would all be large worlds with large rock and ice cores, surrounded by very massive envelopes of hydrogen and helium gas. Now, the first of these to be discovered was 51 Pegasus. This is an artist's impression. This was the first planet which was found orbiting a star, something like the Sun. Before this, some planets were observed orbiting compact objects called neutron stars, which are, of course, very unlike the Sun. And the property of 51 Pegasus is that it's extraordinarily close to its host star. So the distance between the planet and the star for the 51 Pegasus system is only 1% of the Jupiter-Sun distance. So this massive planet, this massive hot Jupiter, as we would now call it, is something like 20 times closer to its star than the Earth is from the Sun. So this planet is now the prototype of a whole family of planets which are described as hot Jupiters. The temperatures at the surface of those planets would be very high. In many cases, those are going to be higher than 1,000 degrees. So really, they are extremely hot, roasted planets, very close to their parent stars. Now, that was the first of those planets to be discovered. We now know quite a lot about both those planets and other giant planets. Here's a plot of the orbital distance and the planet mass of a sample of extrasolar planets. And in red there is indicated where the hot Jupiters would lie. These are planets that are really very close to their host stars and have masses that sort of fall in the Saturn to Jupiter or the super Jupiter range. And we now know that hot Jupiters are not the most common type of extrasolar planet. You can see the number of dots outside that red circle is larger than the number of dots inside, but you can also see that they're not rare. Quite a number of stars have these kind of planets orbiting very close to them. So one mystery is simply, why in the solar system did we have Jupiter at such large distance? We thought we had a theoretical explanation for that. Here we have a class of stars where actually the planets are much, much closer, where in the solar system story we would only expect to have terrestrial planets. So that's one mystery. A second mystery is related to the shapes of the orbits. So what you have here is just a picture of the orbits of a few of the planets in the solar system and a small number of extrasolar planets. And the one I want to highlight here is this object here, which, as you can see, has an extremely eccentric orbit. At its point of closest approach to the star, it's much, much closer than at the point of most distant approach. And that's in some contrast to the solar system, where all of the giant planets have orbits that are not perfectly circular, but are quite close to circular. So when we see a planet like this, we're seeing an object that in the solar system has an orbit that would be more reminiscent of something like a comet, a very small object which can certainly have very eccentric orbits in the solar system. Again, we can look at the population of extrasolar planets. Here it's shown in a graph of period, orbital period, against the eccentricity of the orbits. So circular orbits would be down at the bottom at 0 eccentricity. And what you can see is that when you go a reasonable distance away from the star, where the star is not interacting with the planet due to tides, there's a very broad distribution of eccentricities that starts at 0 but goes up to very high values. Okay. So again, it appears that Jupiter's orbit, which is near circular, is not unknown among observed extrasolar planets, but it's by no means the most common situation that we seem to see in the extrasolar planet population. And then finally, and most recently, you can ask, what about the tilt or the inclination of the orbit relative to the equator that is defined by the star's rotation? So you can imagine that take the sun is rotating, and then that defines an equatorial plane, and the planets in the solar system all orbit quite close to that equatorial plane. They're not exactly in that plane, but they're quite close to it. Now, for some hot Jupiters, we can measure that alignment or lack of alignment between the equatorial plane defined by the stellar rotation and the orbit of the planet, the hot Jupiter, which is orbiting very close to its star. And what we find is that if the star itself is relatively cool, so that would be to the left of this plot, the planets that we see, the hot Jupiters that we see orbiting it, are typically quite close to the equator, as we would have expected from the solar system. However, if we go to hotter stars, there's actually a broad range of that inclination. So in some cases, the planets are very tilted with respect to the equatorial plane. In some cases, perhaps, the orbits are polar. And in some cases, perhaps, the orbits are even retrograde. So the orbit has been, if you like, completely tipped up compared to expectations. So this result is perhaps the most surprising of all, because historically, it was the fact that the planets all orbited in a plane, which gave the original ideas that they formed from a protoplanetary disk. Okay? The flat geometry naturally suggested that they formed in a disk-like structure. But for these hot Jupiters, at least, their current orbits are not like that. They actually can be even upside down, if you like, compared to what they should be. Okay, so why is this the case? Why do we have these close-in planets, close-in massive planets? Why do we have these eccentric orbits? Why do we have, in some cases, these inclinations with respect to what we would have expected for where the planets are? So we've known about many of these things for a long time, for something like 20 years, and we still don't know the answer to that question for sure. However, a possibility, and perhaps a likely possibility, is that much of this complexity is a result of gravitational dynamics that took place after the planetary system itself formed. And this, in fact, would have been familiar to scientists a long time back. If we go back even to Isaac Newton, who started developing the theory of gravity as we now understood it, Newton understood that systems like the Earth and the Moon, where we just have two objects orbiting each other under their mutual gravity, are not, of course, the only kinds of systems where gravity would be important. In the solar system, we have multiple planets orbiting the Sun, and even though the gravity from the Sun is the dominant force that is acting on those planets, the gravity between the planets also acts to perturb their orbits. And Newton, in fact, was worried about this question, and he was worried that the perturbations of gravity from the other planets would ultimately act to destabilize the orbit of the Earth and the other planets in the solar system. Okay? And this is a quote from Newton. Newton worried that perhaps those perturbations would add up and eventually kick the Earth out of its orbit. And this was a long time ago. Newton's suggestion was that ultimately this system wants a reformation, by which he meant a religious intervention, that God would step in to prevent the planets in the solar system from being kicked out of their natural orbits. Now, in more modern terms, if we have a planetary system where the planets are too close to each other, if we try to squeeze a planetary system together, what will happen is that the orbits will become chaotic, and ultimately that will tend to lead to the orbits crossing each other. And once the orbits start crossing each other, generally on a short time scale, either the planets will physically collide, or some of them will be ejected from the system entirely, or perhaps some of them will be thrown into the Sun. So basically something bad will happen in any of those three circumstances. So how might that work to explain what we see? So what we have here is another computer simulation. So this is distance from the star on the horizontal axis. This is planetary eccentricity on the vertical axis. And what we've done here is to consider a system of three giant planets that are placed quite close together, some material which is trying to form terrestrial planets close to the star, and then a disk of bodies which represents something like the solar system's Kuiper belt, icy bodies that are formed far away from the And if we let this go, we see something a little bit similar to that previous simulation I showed. You can see the material in the inner part of the planetary system is starting to collide together and grow larger. Again, the colors are showing the water fraction of these objects. So water is being mixed from the outer region of the asteroid belt to the inner part. But in a moment, we're going to get an instability among the giant planets. There it goes. And so what happened here is that the giant planets had a close encounter, which ejected one of the giant planets entirely and caused the two survivors to develop eccentric orbits. And you can see that in that process, they actually removed almost all of the remaining material in the planetary system. So terrestrial planet formation was going quite nicely in this system, but then we had this catastrophe among the giant planets, and all of that material was ultimately lost. And what you ended up with here were two giant planets, which, as you can see, have quite eccentric orbits. Okay, so you can do many simulations of that process and ask how well does that reproduce the distribution of eccentricities we actually see in extrasolar planets? And the answer is it does a reasonable job. So if you just imagine that most planetary systems that contain giant planets had several giant planets which were fairly close together, so that they would have suffered this kind of instability, then the outcome of that instability would be systems of eccentric planets, and in some cases inclined planets, with properties that are reasonably close to what we see in extrasolar planetary systems. So what we see there could be a result, a conclusion of quite violent dynamics that maybe took place in the first 10 or 100 million years after the system has formed. Now, I should say this is not the only way in which you could produce those unusual orbits that we see. There are other ideas. Some of those involve gravitational interactions not among planets, but between planets and binary stars. And we know that binary stars are quite common in the galaxy. So that's also not an unreasonable hypothesis for what might be going on. Here's just another movie of this same kind of process. So this is a chaotic process, so it can differ between different realizations quite substantially. In all cases, we're getting an instability among the giant planets here, but the exact outcome of that instability varies a lot from case to case. So again, you have the terrestrial planet formation close to the sun is going quite well. We have an instability among the giant planets, but here the other planets are thrown further away from the star entirely, and you can maybe see to the left there, one terrestrial planet actually survives in this simulation. So in this case, not all of the terrestrial planet region was cleared out. We got left in this simulated planetary system with one terrestrial planet, but as you can see, it has a very high eccentricity. So it's nothing like the Earth. It has an eccentricity that's high, and which also changes from time to time due to the gravitational influence of this nearby giant planet, which also survived in the system. So if that kind of idea is correct, if that's how we produced these eccentric and inclined orbits among giant extrasolar planets, a consequence should be that we might be able to see the imprint of that on some terrestrial planets, some rocky planets, in the same planetary system. You might have a circumstance like the one that's illustrated here, where a rocky planet has an orbit that is sometimes circular, but then on a relatively short timescale, by astronomical timescales, becomes quite eccentric, and then it becomes circular again, eccentric again, and has a cyclic behavior like that. And that would have very interesting implications for the climate on such a world. When the world became quite eccentric, the average amount of starlight it received would go down, and so it could enter, for example, in what's called a snowball phase, where all the water on the surface is frozen. Then when the orbit becomes circular and there's more starlight to heat up the planet, it could become a liquid planet with liquid water on the surface. So that's a prediction, an idea. We have not yet observed any planets which would have dynamics such that this kind of interesting climatic cycle would take place. But it's a possibility for the future. Okay, so that was giant planets. What about smaller planets? So by smaller planets here, we're thinking about extrasolar planets that have masses or radii that are significantly smaller than those of Saturn. And one of the results of the last decade or thereabouts is that we now know a very large census of those kind of planets. So this was the launch of the Kepler spacecraft. So Kepler was a mission which stared at a small patch of sky and looked for extrasolar planets that passed in front of their host stars as seen from the Earth. And by measuring the properties of those transits, you can measure in particular the radii of the planets that were in those systems. And Kepler's mission has recently finished, and the final catalogue of planets from Kepler involves something like 4,000 systems. Now, not all of those are real planets. There are probably some false positives among that catalogue, but we think the vast majority of those systems are bona fide extrasolar planets, and many of them are substantially smaller than the giant planets which we've been talking about before. So what did Kepler actually find? Well, the first result of Kepler, and maybe the most important one, was that these relatively small planets, relatively close to their stars, are really extraordinarily common. So in the solar system, we have Earth and Venus. Venus is a little bit closer to the Sun than the Earth, but it's still really fairly far out there in the planetary system. And inside Venus, we just have Mercury, which is really a very small planet indeed. Okay. But in many extrasolar planetary systems, we have small planets, but planets that are still larger than the Earth and Venus, which are really much, much closer to their stars. So in this diagram here, you have the orbital period of the planet, and then on the vertical axis, you have the planetary radius in units of Earth radius. So a planet with 1 Earth radius would have the same size as the Earth. And from the statistics that were accumulated by Kepler, we now know that, roughly speaking, there's 1 planet on average per star with an orbital period of less than 50 days. So in a region where there's basically nothing in the solar system, on average, a typical star in our galaxy has 1 planet. Of course, it's not 1 planet per star. Some stars have more than 1 planet that's been observed. Some stars have none. But on average, it's about 1 per star. So we know for sure that small planets, which perhaps includes planets of the mass and radius of the Earth, are really extraordinarily abundant in the galaxy. So to go back to that Gaia picture of the galaxy we started with 100 billion stars or several hundred billion stars we have in the galaxy, we probably have a similar number of planets all told in the galaxy. Now, for most of these planets, all we know about them is what was measured by the Kepler satellite. And so what we have is actually almost entirely shown just on this one plot. So things we know well is the orbital period of the planet, and we also know reasonably well the radii of those planets, because those are the things that Kepler directly measured. We can also say something reasonable about the properties of the star itself, about which the planet is orbiting. What is the star's mass, and how does that stellar mass compare to the mass of the planet? But in most cases, that's really all we know. However, there's a smaller number, a much smaller number, where we know not just the radius, but we've also been able, with various mechanisms, to measure the mass. And in that case, we can learn something extra. We can obviously calculate the planetary density. What is the density of the material, on average, that makes up that planet? So let me show you a plot of what the main result was from Kepler, and also some ground-based observations of extrasolar planets. So this is a very complicated plot, because there's a lot of systems which are sort of clustered all over this diagram. So I'll sort of go slowly and try to explain what we think we're seeing here. So on the horizontal axis, we have the planetary mass, and this is 1 Earth mass here, up to 30 Earth masses on the right. And then on the vertical axis, we have the planetary radius, again going from about 1 Earth radius up to several times the radius of the Earth. And what's shown here are some planets in the solar system, some extrasolar planets, and then some theoretical curves showing what planets of particular composition, what kind of density those planets would have, and therefore what radius they would have for a given mass. So to orient you here, here's the Earth at 1 Earth radius and 1 Earth mass. There's Venus with fairly similar properties. And then on the upper right there, you may be able to see Uranus and Neptune as representatives of this sort of mass and radius of planet in the solar system. So there are some sort of familiar objects, or potentially familiar objects, here on this diagram. So to the lower left, near where the Earth and Venus sit in this plot, you can see that there are some extrasolar planets. Now, the Earth and Venus are largely rocky planets, and so it's reasonable to assume, based on the fact that their densities, their masses, their radii are similar, that on the left-hand side of this diagram, we're dealing with rocky planets which maybe have compositions somewhat similar to that of the Earth. Likewise, if you look in the upper right, there's actually a larger number of objects there that have masses and radii which are quite comparable to those of Uranus and Neptune in the solar system. So those may well have compositions which are similar to Uranus and Neptune, so they probably consist of a core of mostly icy material, but perhaps rocky material as well, and then they have an atmosphere that is mostly made up of gases like hydrogen and helium, which is producing the relatively large radius and the relatively low density of those objects. So those are the familiar objects that we have in this diagram. However, there are also a very large number of objects that don't fall into those two classes. Okay, so in the solar system, we do not have any planets that have 4 times the mass of the Earth, but as you can see in this extrasolar planetary sample, we actually have a very large number of such planets. So these planets are sometimes described as super-Earths or mini-Neptunes, and they occupy a region of mass and radius, and therefore density, which is not represented by solar system objects. And we don't really know what those are. So the curves that are shown here are theoretical models showing what sorts of radii planets of different mass and different composition would have. So the red line at the bottom is a planet that's made up of 100% iron, and that is basically the most dense object you could imagine forming in a planetary system. So this would be something like a very massive version of Mercury, which has a very high density. So that's that sort of lower boundary, that's the densest kind of object you have. And then as you step up through these theoretical curves, you have planets with different compositions. Smaller amounts of very heavy materials like iron, and larger amounts of lighter rocks, such as we have on the Earth. So that can give you a lower density object, but then you can also make a lower density object by making it, for example, entirely out of water. So the blue line here shows the predicted radius mass relation for a planet that is almost 100% made of water, a pure water world. As I said before, water is actually a very common material, we think, in protoplanetary disks. So it's not actually impossible that in some cases you might be able to make a world that is mostly made of water. And then if you go to the far left of the diagram, you have a track which shows a planet that's basically got no heavy materials at all. It's just made of hydrogen and helium, and that, of course, produces the lowest density planet that you can have. So what you can see here is that this very large number of super-Earths and mini-Neptunes really spans this density range, and just from looking at this plot, and actually from anything we've really determined to date, we can't really say what these objects are made of. Okay? Some of them down the bottom may be rocky objects like the Earth, some at the top maybe things rather like Uranus and Neptune, but the ones in between, exactly what they are, we really don't know. So that's where the situation is with these lower mass planets. They fall in a region of parameter space where we do not have solar system analogues to really guide us, and so we are forced to make hopefully informed speculations about what they are. So I would say the most likely hypothesis is that forming planets of a few times the mass of the Earth is rather easier than we thought previously, and that then when those planets form, the amount of gas that they can capture from the protoplanetary disk can be quite variable. So in some cases we can produce an object of a few Earth masses that's mostly rock, that would be a super-Earth. In some cases that same planet can perhaps form a little bit earlier, can capture a modestly significant hydrogen and helium envelope, and that gives it a large puffed up radius and a much smaller density when we observe it in this radius-mass relationship. So that's perhaps the most likely hypothesis, but then there are other possibilities I've already mentioned. It's possible that some of these worlds truly are much more exotic, and for example, that some of them are in fact made up almost entirely of water. We just don't know, we don't have the observations to make that determination at this time. So with those observations to guide us, can we start to answer those large questions we posed at the start? How common is the solar system? How common are potentially habitable planets like the Earth? How common are planets that might have life on them in the rest of the galaxy, given this very large number of potential stars and potential planetary systems which we have to work with? So the first question is, how common are solar system analogues? And so here's a plot showing now a large sample of extrasolar planets, basically all of the systems that we've known and confirmed to this date. So this is distance from the star on the horizontal axis again. This is planet mass on the right. And I've put here the Earth and Jupiter to show where some familiar planets in the solar system lie on this plot. And what you can immediately see is that even though we've observed some small planets, some planets with masses and radii that are comparable to the Earth, most of those have been orbiting significantly closer to their host stars than the Earth does in the solar system. So the Earth here sits in a rather lonely region. We don't know that there are not many planets in that region, but so far Kepler and the other missions that have been devoted to finding extrasolar planets have not had the sensitivity to see those objects. So the question of how common is something really like the solar system, you can immediately see is one which we cannot really answer at this time, because we simply haven't got any idea, any clear idea, how common is an Earth-like planet at the Earth-Sun distance around another star. For Jupiter, on the other hand, the situation is better. You can see that Jupiter there, in terms of how far away it is from the Sun, and its mass falls in a region where there's sort of a cloud of extrasolar planets. There are actually quite a large number of systems we've seen with massive planets at about the distance from their star as Jupiter. So for this question, the best guess at the answer for the moment is that our giant planets actually seem to be fairly typical, at least in terms of their distance from the star. Forming giant planets at several times the Earth-Sun distance is probably a common outcome around stars in the galaxy. So in distance, they're fairly typical, but the solar system giant planets do appear to have unusual orbits in the sense that the solar system orbits are really quite closely circular and lie quite closely in one plane. And it seems that in particular the eccentricity of the orbit, the near circular nature of the solar system giant planets, is really not the typical outcome of planet formation in the extrasolar planetary systems that we see. Then turning into the closer in planets, all we can really say is that planets that are closer to their stars than the Earth, and which are often more massive than the terrestrial planets that we see in the solar system, are certainly extremely common. So those systems where we have close-in planets with perhaps relatively high masses, several times the mass of the Earth, that may actually be the most common outcome of planet formation. Still not clear, as I say, whether there may not be also a very large number of systems where we really have like Earth-type planets at Earth radius. For the moment, we simply don't know that. How did those planets form? So how well does the theory that was developed in the 60s and later for the formation of planets, how well does that stand up to what we've now seen in extrasolar planetary systems? Well, I think in many ways it stands up quite well. We've not really observed any planetary systems whose basic formation process could not be explained as an extension of the model that was originally developed for the solar system. So the same physics, the same physical processes, we think, governed the formation of extrasolar planetary systems as governed the formation of the solar system. However, when we look at extrasolar planetary systems today, it appears that what we see has been very strongly modified by various types of dynamics that took place after the main formation epoch of the planets. I emphasized one of those already in the talk, the possibility of gravitational interactions among systems of multiple giant planets, but there are other kinds of interactions that might also have taken place at those early times. It's possible that some of the planets interacted with the gas and the dust of the protoplanetary disks within which they were formed, and that those interactions either brought them closer to their stars or actually pushed them further away into the outer regions of their systems. So it seems that the formation, if you like, is somewhat similar, but actually what we see has been modified, has been scrambled to a large extent compared to what happened at the earliest times. And we think some of that probably went on in the solar system as well, but perhaps not to such an extreme degree as happened in many extrasolar planetary systems. Now, what about habitable planets? Well, this is a tricky question, because to ask how many habitable planets there are, you first have to decide what we really mean by habitability and how we define habitability for an extrasolar planetary system where we can only measure the properties of that system to a relatively poor degree at the current time. So the simplest definition and the most common definition is that we would say a planet is potentially habitable if the surface temperature of the planet is such that liquid water could persist on that planet throughout the lifetime of the system up to the current day. And a number of planets have been seen which meet the definition of habitability according to that definition. So here's a plot that shows the amount of sunlight, the amount of starlight that the planet receives, and then on the vertical axis is the temperature of the surface of the star. So on the bottom you have relatively cool stars. These would be red stars, low mass stars in the galaxy. Towards the upper part you'd have stars that are more like the sun. And these curves here, the blue curve and the red curve, give estimates of how far away from the star you could be and still be in this region where you could have liquid water on the surface. So if you get too close to the star, it would be too hot for surface liquid water. If you go too far out, it would be too cold for surface liquid water. And as you can see, there's a number of plots of planets which fall in this sweet spot. So it's a small number of candidates, depending on how you count it. There's maybe 10 or 20 such planets known, but there are at least a number of systems which one might hope to investigate more in the future and see really whether the surface conditions are amenable for habitability. But as I say, that's just one definition of habitability. That's the most simple thing we could think about, having liquid water on the surface. We know that there's a lot more to habitability than just water. So I come from London, and if water was the only thing to do with habitability, London would be the most habitable city on Earth, okay? And it's probably not true, unfortunately. we know various things, okay? So if we just think, and it can go in either direction. So if we ask, what would make it harder for a planet to be habitable, there are some properties of the Earth which appear to be very important for current life on Earth, or the formation of life on Earth, which go beyond just having liquid water on the surface. So one of those is the existence of the moon. So the existence of the moon, the fact that Earth has a large moon, stabilizes the Earth's axis against perturbations from the other planets. So at least the climate on Earth, over very long timescales, would be quite different if we didn't have the moon. So how common is it to have a large moon, like our own moon, around a planet the mass of the Earth? We obviously don't know that question, certainly from an observational point of view at all, and we don't even have a very clear answer to that theoretically. Then going beyond that, on Earth, the existence of a stable climate over very long timescales is very closely connected with how carbon dioxide behaves in our atmosphere. And so volcanoes play a crucial role in that because they allow material from the inside of the Earth to come out into the atmosphere. And then on the other part of the cycle, carbon dioxide in the atmosphere is ultimately washed into the oceans, forms rocks, it's taken up by living things in the oceans, and that material is then subducted back into the Earth at plate boundaries. So there's an argument that the habitability of the Earth on long timescales depends on having plate tectonics. Okay. Now, how common is that sort of thing in extrasolar planetary systems? How common are large moons? How common is plate tectonics? These are obviously questions which are very, very difficult. For the moment, we certainly can't answer those questions in an empirical way. We just don't have the observations to say anything about that at this time. And then in the other direction, as I already mentioned, there are potentially habitable places in the solar system where there cannot be liquid water on the surface. So Europa, Enceladus, some of these other bodies where we think there might be subsurface oceans. These are things where, by the definition of habitability just based on liquid water, we would say they were definitely not habitable. But in fact, it's conceivable that even today they have life in the solar system. So how can we move forward? What's next in this topic? Well, one aspect that I'm particularly interested in is whether we can step back from observing planetary systems, often billions of years after they formed, and actually catch them in the act of forming within their protoplanetary disks. We've already said that we think that many aspects of planetary system properties might be altered after the time they formed, perhaps due to interactions with the protoplanetary disk or due to interactions amongst the planets themselves. So if we could catch a sample of planetary systems at an earlier stage, we would be able to say something about how they formed before their properties were scrambled and changed by this later dynamics. And this is an image which was just released actually this week. This is a young star surrounded by a disk that's being imaged in the near infrared. So it's wavelengths that are a little bit longer than optical wavelengths. And what we think is being seen here is a star in the center, which is masked out. It's surrounded by a gas disk, and then there's a source there, which is a candidate giant planet in the act of forming within the disk. What you can maybe see here is that the planet, the gravitational interaction from the planet, appears to have sort of carved out a structure, a hole, a gap within that protoplanetary disk. So this is a new observation. Still remains to be seen exactly what's being seen here, but there's a lot of effort going towards imaging these young disks, these young planetary systems at very early times, and so it's reasonable to think that within a year or two, we may start to have a sample of planetary systems which have really been caught in the act of formation. And that would be tremendously useful for understanding really what is going on, at least in the late stages of planet formation and the formation of giant planets. At least for the moment, it would be very difficult to make a similar image where we could see the formation of planets with masses more like the Earth. We're restricted really to just looking at giant planets. Also exciting is the recent launch of TESS, the Transiting Exoplanet Survey Satellite. So this is in some sense a follow-up mission to the Kepler mission. So TESS was recently launched earlier this year. It's a small satellite which will scan almost the entire sky looking for extrasolar planets. And it uses the same technique as Kepler. It's searching for the transits of planets which move across the face of their stars and cause a small dip in the starlight as they block out a piece of the starlight around the star. So TESS has been launched, and the key thing that TESS will do is that because it covers the whole sky, it will hopefully find the planets around stars that are bright and relatively near to the Sun. And that's key because most of the planets that were found with Kepler are very faint stars, and it's difficult to follow up those observations with additional observations to learn more about the planetary system. The test targets will be around bright stars. They will be the best systems for following up with future observational facilities. So the hope is the tests will identify potentially habitable planets that are in this region where liquid water could potentially be present on their surface. They'll be around bright stars, and then in the future it will be possible to follow up those observations with additional observations that can actually probe the atmospheres of those planets and look perhaps for signs of life on those worlds. So those are near-term future things. In the longer term, as I say, we hope to actually observe extrasolar planetary atmospheres of planets that are potentially habitable. And if so, what we would hope to see is, in some cases, perhaps the same kinds of atmospheric signatures that on the Earth are signatures of having existing life, present life, on the planet. So here is a representation of what the spectrum of the Earth, the distribution of light at different wavelengths, would look if it was seen from afar, going from optical wavelengths to the left out to infrared wavelengths on the right. And these dips that are shown in this graph here, in this spectrum, are the fingerprints of different chemical elements in the atmosphere, different molecules in the atmosphere. And so you have here things like water, oxygen, ozone, methane, carbon dioxide, and so forth. And some of these, particularly oxygen and ozone, on the Earth are only present in large abundances because of the fact that we have life, we have photosynthesis, and so forth going on in the Earth. What we hope is that perhaps if nature is generous, we would be able to observe something similar around extrasolar planets. So first of all, we'll be able to observe this spectrum. We think that's technologically feasible, but it's extremely ambitious. And so in the best case, missions that are being planned now, and which therefore will be launched 10, 20 years from now, those are the kind of space missions which might have the sensitivity to start making measurements of this kind of data. So we hope we might be able to observe this, and then moreover we hope we might be able to understand these atmospheres well enough to know that if we see a spectrum like this, it really points to the fact that that planet has life, rather perhaps than some strange geological processes which are giving rise to oxygen and ozone in larger amounts than we would think would be possible based on the Earth. So I think here we need several things. We need to understand atmospheres better, perhaps starting from atmospheres that are not habitable at all, but which are just alien atmospheres to the ones we know in the solar system. So we need better understanding. We need to actually build these probably space-based facilities that could actually make the observations. And then we probably also need a little bit of luck. We probably need, for some planets close to the Sun, which can be observed in great detail, to have relatively clean signatures that either indicate they do have life present or have no signatures that we can see of life. Yeah, so the ejected planets would basically be floating through space. So we think the galaxy probably contains a large number of ejected planetary systems, perhaps even as many as one planet per star. But we don't really know of any way in which those planets could be gravitationally captured by other stars, at least at the current time, and therefore form a new system of planets. It might be possible for some planets to be exchanged between stars, or at least comets to be exchanged between stars during the formation process. Yes, so the stars for these lower close-in planets span a wide range. So some of them are solar-type stars. Many of them are lower-mass stars, simply because lower-mass stars are more common in the galaxy. Now, for more massive planets, for giant planets, we see that those planets are most commonly found around stars that have relatively large amounts of heavy elements in them. However, for the lower mass planets, they're so common that they appear to be present around basically stars with a wide range of metal content. So there doesn't appear to be anything very special about the stars themselves.
Thank you for the lecture. It was a pleasure. I have a simple question. Do you consider selection bias in this kind of work? I mean, Kepler and Harps, they have their own pluses and minuses. Kepler cannot see planets that are far away from the stars. Harps cannot see smaller planets. Can we actually be sure that this distribution is the true distribution of the exoplanets, or it's not? It could change after TESS starts working, or I don't know, James Webb if it launches, starts observing those planets. Thank you.
Yes, so I think for giant planets, we can be reasonably sure out to maybe the distance of Jupiter. So for giant planets, we're sensitive enough to really have a fairly complete census of what giant planet systems look like out to about the distance of Jupiter. For lower mass planets, the selection biases are still enormous. So all we can really say is that there's this large population of small planets, which is very different from what we would have expected in the solar system. We can't yet say whether Earth-like planets at 1 AU are not also very common. It's quite possible and maybe even likely that they are common, but just at the moment we can't say. And certainly, if we ask how common is a Earth-like planet with a giant planet like Jupiter, about that there's almost nothing which we can say.
Hello, thank you very much for your lecture. It was very interesting, and I have two questions, if I may. And the first one, I want to begin from the start, and from the large gas and dust cloud that began to gathering together. And how did it happen that it gathered not into one large object, but into a great amount of separate distant stars? That's the first question. And the second question is, I'm a big fan of Interstellar, and as I can see, we now observing the systems of quite common stars and planets, and how can it even be possible that we have an uncommon star like neutron star or like a black hole with planets orbiting around these stars? Thank you.
In general, we think that the gas clouds that form stars are not very smooth. In fact, we observe that they're very clumpy. And so the fact that we form clusters of stars rather than a single large object is ultimately due to that clumpiness, that turbulence within the gas that forms the stars. So because of that, there's a tendency for, as the gas collapses, it to fragment on smaller and smaller scales, and that's ultimately what gives us this cluster. Now, the question of whether we could have planetary systems around really exotic star types is a fascinating one. And actually, the first planetary system that was discovered was around a neutron star. Okay, and that has several planets orbiting a neutron star that ultimately formed in a supernova explosion. So when that happened, there was great excitement that maybe many neutron stars have planetary systems. But it seems that actually they're rare. And that perhaps says something about the formation mechanism of that system being itself fairly rare. So generally when a star explodes as a supernova, most of the mass is of course lost. Any pre-existing planets are ejected. And then maybe what happened is that some material fell back, formed a new disk, and new planets formed out of that. That's one idea. And so I guess the observation would suggest that that process is fairly uncommon. As for black holes, that would be even more exciting. I guess at the moment there's really no way we could possibly observe such a system. So that in principle such systems could exist, but we wouldn't know it at the moment.
Okay, so let me start with the second question, because Star Wars is great fun. So yes, something like Tatooine is possible, and it's been observed. In addition to the large number of planetary systems around single stars that Kepler saw, there's a small number of mostly very close binary stars where we see planets orbiting the entire binary. And the planets that are currently known are not Earth-like. They're more like the mass of Saturn in some cases, but there's no reason in principle the way that there couldn't also be lower mass rocky planets in similar systems. As for the metallicity of the star, for giant planets, having more metals in the star increases the probability of having giant planets quite significantly. And having very few metals really makes it unlikely that we would see giant planets. For lower mass planets, that effect is much less strong, or maybe not present at all.
Hello. I wanted to ask about Venus. You explained how water was delivered to Earth by gravitational covered with ice, but why does Venus have no water?
So I think that's in part saying something about also processes that might lose water from planets. So if you have an atmosphere with water in the atmosphere, stellar radiation striking the upper part of the atmosphere can break up the water molecule, and then the hydrogen, which is a very light gas, can escape to space. And so that actually gives another aspect of a planet which might be important for habitability, because for the Earth, having the Earth's magnetic field in some sense protects the Earth against that process. But if you don't have a magnetic field, or in some other circumstances, it can be quite possible to lose quite large amounts of water to space over billions of years, simply by breaking up the water molecules from stellar radiation in the atmosphere.
Thank you for the lecture. Is it possible that a brown dwarf forms after the main system and the star was formed, like large objects like Jupiter or hard Jupiter?
Yeah, so the possibility of having brown dwarfs forming in the same systems, observationally, we don't find that brown dwarfs are very common in close orbits around stars. So for reasons that are not fully understood, it does appear that there's something of a gap between the distribution of planets and the distribution of stars. So we see large numbers of brown dwarfs, but they're either in much more distant orbits, or they're completely isolated in the galaxy. So I think for the question of looking for life, I personally take a very open view. Right? Clearly, we know that there are many possible sites for life, but we really know almost nothing about how life got started on Earth. And so it's perfectly possible that was an extraordinarily rare event, or it's perfectly possible that it was very common. We really don't know. And so I guess my hope would be that this is a question we can answer from actual observations, right? We can make some progress in looking at other planets and trying to see, do their atmospheres look like anything like in the solar system, or are they completely alien? And if they're completely alien, we may have a lot of trouble really understanding what we're seeing. So in that sense, it may be very difficult and challenging. But it's also possible that we will find a world that really looks a close twin of the Earth. And in that case, perhaps we could make a more robust inference. As for what we could actually see, if we were really able to see these things with our own eyes, much of the energy which is being radiated from protoplanetary disks is in infrared wavelengths that we wouldn't see. But we would see the light from the star, which is scattered by small dust particles. And in fact, when we showed an image from the Hubble Space Telescope, which was basically invisible light, and so if you had enough sensitivity, if you had the sensitivity of the Hubble Space Telescope, you would actually see that. You would see that image. So there would be something to see if we were fortunate enough to be in one of these, or close to one of these star-forming regions. So the simple answer is that we don't know. But I'm a professor, so I'll give a longer answer. So in the solar system, there's quite a chain of events which gave rise to, we think, the presence of water on Earth. Okay? And I think that specific chain of events, you would have to say, is unlikely because it involved various aspects of the solar system's architecture. However, probably there are other ways in which water could also be moved around within a planetary system. So it's likely, I think, that you could produce at least reasonable amounts of water on terrestrial planets fairly commonly, even though perhaps the exact way that happened was a little bit different from in the solar system. So I would say a key factor would be perhaps having both low-mass planets and also some giant planets which can excite the eccentricities and excite the orbits of water-carrying planetesimals and asteroids and cause that material to sort of move radially through the planetary system.